So you're welcome to get started whenever you like.
Okay.
Yeah, I'll get out of your way.
Okay, so oh, this is not projecting. This is just recording, I guess. This is not projecting, right? It's just recording.
It should project a little bit in the back
Okay.
of the room, but yeah, it doesn't sound particularly loud.
Okay. Yeah, it must be projecting in the back because everyone's sitting in the back, so it must be where the audio is better, I guess. I don't know. Got her PhD at the University of Quebec and did a postdoctoral study. And I was introducing someone and I admitted some of their words and they got very annoyed with me. So I got to here to read precisely the description. She received the Academic of the General of Canada. She was awarded Magazine's 2015 100 Inspiring. And she is currently a Communication Society Distinguished Lecturer. So,
mine, so I hope it's recording well.
Sorry. Logged in, it's not showing the screen. So let me fix that for you. I apologize.
No problem.
introducing so many words. I didn't mention all.
There you go. Now you get it.
Okay, perfect.
I missed the wrong one.
Okay, thank you very much, everyone. So my name again, Besma Smida. So I'll be talking today about full-duplex wireless and particularly full-duplex integrated sensing and communication. So, so the overview where I come from. So I'm at the University of Illinois, Chicago, and I'm an associate professor at ECE department. So, so UIC, we're roughly 34,000 students. It's an urban environment, so it's what we call the West Loop in Chicago. So it's really an urban, like in downtown, very walkable for everywhere. And then we are part of University of Illinois system. We are the second biggest campus after the Urbana campus. Then you have Chicago, and we are the largest Chicago Metropolitan University. We are also ranked R1 with very high research activity. So I have a little bit of picture there of the fall, thinking that you don't get that much color here, but I was surprised to actually see you have already the color. But again, you have to be honest and you have to put a picture of Chicago in the winter. And that's the picture on the right, so be fair. It's not all fun and warm. It's very cold in the winter too. Okay, so I'm part of what we call the nicest lab. So this lab we created when I joined UIC. And I'm very happy to see I'm a part of a lab that most of the director are actually female faculty, and we all do research in wireless communication. So we go from all information theory, and that's Professor DeFroy, to Nenetti, all the way to network and building, and that's Professor Seperbro and Professor Kunu. So those are more into network communication. And I will be more a little bit in the middle in communication theory, where sometimes I do a little bit of information theory, but I also go all the way to that when we do the full duplex, you need to kind of see a little bit what's happening in the RF side. So I'm a little bit in the middle of communication theory into with that is 6 level. So I was, as I said, there, and I was roughly 30 students. Most of the funding, with exception, comes from when we have like so the nicest lab at UIC. bit myself that Robert did not mention, so this little bit. So I will not say much except that I traveled a lot. I'm born and raised in Tunisia, just a little bit, give you a little bit of actually degree in master, and I worked in master in and I moved as and I keep my webpage up to date, so to contact me to get through the webpage. Okay, so let's get to the technical part. So there will be a little bit of full-duplex before the integrated sensing and communication. There will be full-duplex part, and the emphasis approaches sensing. And I will tell you right now, the emphasis today will be definitively the full-duplex and, of course, the algorithmic part of it. But there's a lot of full-duplex there. That's how we get to this field. So I would say in terms of motivation, and this is for multiple reasons, but I would say one of the biggest, I will see the chapter of integrated sensing and communication will be vehicular network. This network already, the cars are communication part, so to do some integrated sensing and communication. And we'll talk what we mean integrated communication. Two techniques, they're very, even in with, and you notice here in the right side, using our system. And I will talk about millimeter waves today, so that's the last row of that table. And notice that you have already the radar already using that bandwidth. And of course, we have the 5G. We have there, so I will be one of the adapter of this sensing if you can. But then again, it does not lead to the network. Extract paper free where I present could so it's capturing so when you are using communication devices this interaction having no that does act information. That's really a possibility to integrate those two. So I tried when I started giving presentation to what have been done before. I have to tell you today I gave up. There's so many publications and reference that I admit I cannot do it. So I thought of many ways to classify prior works. And I would say that also shows maybe the complexity, but also what we're talking about when we say integrated sensing and communication. I would say in the absolute level for someone who's like more like square thinking, even using the same antenna for sensing and communication could be counted as integrated sensing and communication. Sharing anything between two systems could be considered part of sensing and communication. But of course, the more serious way is actually to really reuse a lot of part of those two equipment. And then, of course, push it even further. The waveform itself, what you're sensing, what you're sending as a signal could be used for both or used for one, used for both. So that's when you have really communication. So because of that, I would say, I mean, I have this old do integrated 1961 is a good way to say it's if this is information embedded in the radar. So sense. As it as a transmitter, right, to make those our airspace, but you like complexity as much, and a little bit of signal processing too is involved. When we classify integrated sensing and communication, you will see in the middle on the field, especially There's a lot of tutorial paper. There's a lot of classification. One of the popular one is it communication-centric or is it radar-centric communication? And usually what that means, am I having a communication system adding sensing to it, or I'm having a radar system and adding communication to it, okay? Or am I just starting from scratch and trying to converge those two together? So there's a category. For this presentation today, I decided to kind of split them into one, what I call coexistence, and coexistence in a sense, non-overlapping resource allocation, like being adjacent, overlap, try interference, so that you can some kind of time sharing, stuff like that. But also there is a push to actually get them within the same bandwidth, and that's what we'll be talking about. So there are some few recent studies that we use what we call full-duplex, so that's the FG there, and we'll talk about it today. And then there is the second category of, as I said, using the same waveform is the same waveform that it's used to sense. So you send it, you sense it with the information that's included as a communication, okay? And today we'll be considering OFDM. There's a lot of study there, but I think for the topic of today, the focus will be on OFDM. So this is the closest, I would say, to the setting we worked on, and I want to kind of go a little bit deeper into. So this is integrated sensing and communication, what we call monostatic half duplex. Okay, so the plan here, if you have the base station on the left, so you have all your MIMO antenna, and the base station is sending data to the user right side. And then within that, you have what we have this target of black dots. And then, of course, you have target that they're not of interest will create what we call in communication some multipath, direct path from the transmitter and receiver, okay? And then if you do that in a half duplex mode, that means that for some part of the time that's in the downlink, you're sending the data signal for the user. So the base station on the left sending data signal to the user, but then to listen to the echo, that's how you do your sensing. So you send the waveform, you listen to the echo reflected back, and that's how you can get the direction of arrival. You get the range by seeing how far, how long the delay, and even the Doppler would can give you the speed. So then you need to get silence for time and then just wait for the reflected signal to come. And that's why we call the half duplex. So we're not really listening and sending at the same time. Of course, the limitation right there, and that's is you will reduce data rate. So listening, you're sending data. So you're losing in terms of data rate, okay? So if you want to add this sensing service in a communication system that exists there, you're already reducing your data rate right there, okay? And that's when we get a little bit in the idea. So I will, for the next slide, a little bit talk about what is this full duplex, and then we'll kind of merge it with the integrated and sensing communication. Okay, so I think one of the motivation, of course, finally kind of make it kind of not still in study for 5G to have that full duplex. And then, of course, we have also the vehicular network there. So it's kind of one of the motivation, of course, to see that it's kind of make it there, but there's still some challenging related to it. But I would say fundamentally the full duplex idea, and this is for not necessarily sensing, but for communication too, is if you have a transmitter and receiver, and then they're talking to have a bidirectional communication. And by the way, all communication are bidirectional. Even if you're just watching a video, there's always feedbacks going in the other line. So it is always uplink and downlink all the time. So usually to manage to have those two links happening at the same time without necessarily interfering, we do what we call, what you see here, the TDD, the time division duplexer. So one, you send, you listen, you send, you listen, transmit, receive, and you switch. Or we do it through FDD, frequency division duplexer, which is we use for uplink and downlink two different frequencies. So they're not overlapping in spectrum, but they're happening at the same time simultaneously. So full duplex is about saying, I will use transmit and receive at the same time, at the same frequency, okay? So that's a little bit the idea of full duplex. So basically, me talking and listening at the same time in some sense. So what makes the difference though here? I would say the main big difference is how high the transmit signal compared to the received signal. So in general way in communication, we always deal with interference. So that's not new. We always have some interference. Band full duplex, the big challenge is the interference is much, much, much higher than the design. What you're sending did not get into the path loss of the channel. There's no attenuation whatsoever. But what you receive is a signal that propagates all the way from the transmitter, the other end, all the way. So we're talking about 100 dB. So audio signal, I would example in my talks that the audio signal is like someone whispering and an airplane landing times. That's the level of 100 dB difference. So it's really a much larger interference that really you have to have new tools to deal with. So it's something, oh, I'm sending the signal, so I know it, I can just subtract it. Theoretically, yes. You know what you're interfering with. That's your self-interference. That's what we call self-interference. So your transmitter is interfering with your receiver, but it's much more serious than let's subtract it and use it. So the technology, the challenge is more serious than that. So, and then this, of course, you can do it with one antenna, two antennas. So, and we talk about that. So just to give you a little bit the level of what you're talking about, if its transmit is around 30 dB and some antenna isolation, either because you have a circulator if you're using the same antenna, or if you have a little bit of distance between the two antennas, especially in your base station, you can consider you have like a meter or two difference between what you're transmitting and what you're receiving. I think you still have a difference between the interference in red here and the desired signal of around 100 dB, okay? So that's the challenge for full-duplex. That's why we're not doing it, because we, in terms of spectrum efficiency, we would like to do it. We will save the spectrum. We can increase the data rate for everyone if we can implement full-duplex. So how to do with the self-interference cancellation? So as I said, because of this huge level of interference, we usually needed to do in different steps. So the first step is what we call the propagation or passive cancellation, okay? So in the case of one antenna would be circulator, cross polarization, one antenna transmitting one polarization, receiving other. It's not really very applicable for cell phone, but it's still there. And then of course you have a lot of directionality or beamforming. You direct the beam of the transmitter away from your received antenna. So the received antenna get like the null instead of getting the huge power. And you make sure that the power is getting to the user that you're sending to. But that's not enough. Actually, you will need to add a second level, a second domain cancellation, and that's what we call the analog RF cancellation. So once you kind of protect a little bit your amplifier by doing some passive cancellation, now you need also to get to the analog part. So usually the analog part is because you know the signal, so you recreate this, the self-interference signal, and this is when you subtract it, but you have to do it at the analog level. If you do not do that you wait for it to get to the digital level, usually by doing your analog to discrete communication or quantization, your quantization error or clipping errors will just completely kill your signal. So you really have to do that at the analog level. And then, of course, as I said, which have been done before in communication, cancellation. Then again, so the low compound cannot ignore those. This interference below cancel them. Makes them very high. Showing all this technique, I'm giving you hope. So we have tools. I'm not scaring you out of having so many steps to get to the interference, self-interference, but we are there. So, so what I have here in the red and underlined. So underline is some of the work what we have done in self-interference cancellation, but I have like slide for each one of those, so you can have a sense what you have cancellation. Red are the one that we'll be using, and a little bit of the one in underline we'll be using for integrated sensing and communication. Okay, yeah, this is kind of roughly the plot if you add some analog or kind of combination, and then you have the. Okay, so my first approach, actually, this was when I just started working on full-duplex. So the first one was when I joined in, there was a little bit of push from communication theory people saying, okay, why we need full-duplex? We can add more antenna, we have the same gain, MIMO give us the same gain. So of course you want to push a little bit. So then I decided, okay, let's make it the same. I'm sending and receiving the same time over the same spectrum, but I'm also using the same antenna. Let's see how far we can go with single antenna, the same thing. So we do not have to deal with that. So to do that, as I said, usually you have a circulator. So that's you have the transmit and receive. So the circulator adds a little bit of isolation or reduction of the leaking between the two, but usually it's very small. It will not solve actually the problem in band full-duplex. It will be just too small. So what we did actually, and this is part of when you get a little bit closer to the RF part. So we usually have those antenna perfectly matched to the circulator, the famous 50 ohm. So we make sure that everything is matched to maximize the input power, received power. So what we did there is we actually replaced that perfectly matched classical box into this impedance mismatch terminal. So it's like an impedance that, and you can see the circuit here. We have two bacterial diode that we use there that will actually set up a little bit how much leakage. And the idea, that's why we call it inherent self-interference compensation, is will exist in the circulator from receiver to actually cancel the self-interference itself, okay? And that's what we're doing. So by playing a little bit into the performance of this reflection coefficient here, gamma T, we actually cancel the interference. So the purpose here is to have this I and C cancel each other, and I end up with this green signal as strong compared to the other two as possible. Okay, so I have leakage and I have this reflected leakage and I'm playing to them. Of course, here the idea is just to get opposite sign. It's also the first to invent from actually to have either two transmit antenna, one receive, or two receive antenna, one transmit in the middle. And the idea is if you place them in a certain way, that the first interference received with one antenna, the one that received by the other antenna will cancel each other with like the phase shift. So one at D and one D, the opposite cancellation. The first work to prove that you can actually do in-band full-duplex. That works fine, of course, if you do not have wide-band signal or WebTN signal. If you have narrow-band signal, that would work. Literally, we're shifting them based on the lambda. So if the lambda is the middle of your transmitter, as long as this is small, that will work otherwise. So with that, we focus more. A microchip by adding adjust that negative without much of it. We were actually of a high isolation large up to one. No. We need isolation. So in terms of the digital part, so I said passive propagation cancellation band the digital part. So the big fire and component. The regular system not in the same frequency and match the difference between the direct signal and the interference. how the get rid of it. Bring your sender spectrum with the two frequencies some cells. Then to make sure what we call will manage the self. This we actually did a comprehensive self-interference model. We tried to really kind of all this together and make sure what is most important, what is less important, how much, and depending on the equipment. And of course, when you get in a system that modeling is hard, it's very easy in this case to do machine learning. Okay, we don't know the model, or we learn the model. That's what we offer. So very sophisticated. What we wanted to do different component channel estimation. So we have self-interference, you have your channel, you have the node. The equipment, but it's not. So this is a little bit of the background we comes into the field of integrated sensing and communication. Our other thing we did, okay, the limit step is to add more antenna. There's no not you have. Uh, multiple, which is not a large number. But then you have to consider the self-interference from each transmit antenna to each receive antenna. So that makes you 16 steps that you have to cancel. So to make the system instead of feed. So that with the digital communication and reconciliation helps. You have, we work. Can at the digital level without just for to use, not really sending all the I've been doing in the beginning is this two uplink. At the beginning of the packet that's known to the transmitter and receiver, and then the receiver knows the packet, so knows how the channel is. Different kind of technique. You can fix it at the transmitter with recoding. If the transmitter knows the channel, you can do a lot of technique of equalization at the receiver side. We managed fiction of the. We thought here is actually, instead of using this pilot, especially for in a MIMO setting, that beam is the reflected signal and just kind of detect where the user is, and based on that, just kind of have an assumption and use that to do your beams properly and communicate. Here's massive MIMO, millimeter waves. We will be using hybrid beamforming. I will talk about that, which the number of RF chain is less than the number of the antenna, but it's not one. We'll be considering OFDM at the waveform. The OFDM that it's adapted by the signal. We try to get as close as possible from what we have today, 5G. And then we're trying to detect, to communicate with multiple users, but also to detect the multiple target parameter, multiple targets with multi-parameter, direction of arrival, range, and velocity. We tried at the same time when we're doing that, and this is a big part of the research happening now, to kind of reduce the complexity of the self-interference, because we are relying on in-band full-duplex for that. So that was a target, but clearly we can actually, especially for military application, push that aside and just go for the best performance and accuracy possible. So this is always trade-off that depend on your application. And then I will talk a little bit about the framework, what we cancel, what we maximize, how we optimize, which is, again, it's an open research field. So I can show you what we tried and what we think works. But what is optimally possible, I don't think we have the answer to that yet. So this is a little bit the system. So as I said, this will be digital beamforming antenna. None of times we will be for the user and the target. So forever, we do not define to, and we use the web code book. Search. receiver. I will just highlight. To the matrix. And then is the user. What we can do digitally, what we're doing it digitally. To detect those multiple targets, again, we did not use anything very fancy. We will need to update. I will tell you why. We use just music, very popular algorithm in signal processing to detect. So, and that's what we use. We apply it, and then that's how we get the direction of arrival. And then based on the direction of arrival, to get the range and the estimation, we use just the likelihood function, and we maximize the likelihood function. Again, very common technique, works perfectly well in our setting. Okay. So in terms of optimization, and I think this is one of the, still here. This here. Ratio for all the similar thing, okay? So, and I think this is slightly different from other work on full duplex integrated sensing communication. We did not actually start with getting the beam toward nulling the self-interference first. No, we actually get into maximizing the transmit beam toward the target first. That was our first step. Then the second step is the combination of receivers will be maximized toward this will be minimized. Again, just a tool that we use and it works, which is kind of, we took the ratio of the two. So maximizing this, reducing the self-interference, and we try to maximize the ratio again. So that's another tools that we use because we do not have any, we cannot optimize that problem. All the parameters are linked to each other, okay? And then after that, of course, we did the whole music and then direct this thing. And you have the detail about that in the paper. But basically, those are the two steps. I know that there are other works when they maximize what we call the combined. The beam, maximizing that. We do not work with that, and that's something we should implement and compare, okay? So I will show you a little bit of the simulation result here. So we consider we have 128 transmit antennas, MIMOs, with 4 end users. The base station only have 8 RF chain, transmit and receive, so that's the hybrid part. And then we have MIMO multi-user, 2-user with L2 receive antenna for the multi-user. And then the code book is a 5-bit code book and a little bit of the kind of values. So this is all through simulation, of course. So this is the first result for the radar target sensing. So here we have the range. We have 4 radars, so 2 users, and the rest are the passive radars. So you can see here the range, direction of arrival. It's reasonably very well considered the situation. And then we have a maximum range of 80 meters. We also did some tracking of the target. So when they're moving around, of course, the worst case if they move in circles, so they keep changing the data all the time. So that's what we consider, depending on the delta step, how fast they will go. And then we try to kind of mimic a model. We love actually to have a more realistic model for the movement of target, but we did not find that at the time of this publication. So then we make kind of user running around and then try to predict and track. It works reasonably well for all the, of course, when you go faster, the error is higher, but it gets better when you have higher transmit power. In terms of the data rate, so I said that the sending user also detecting, so we want to make sure that detecting duplex, so this is versus if you keep same times. To use so use the still are able to have a huge gain compared to the try to do a multi-use communication, making sure that the Full-duplex part works well in terms of beamforming and analog constellation. The whole thing and make sure we have a certain accuracy for the target in terms of range, velocity, and direction of arrival. Again, as I said, we try to limit the hardware complexity in the analog self-interference, and then to jointly design this analog and digital beamforming and the analog self-interference constellation, all units centralized. And then, of course, we have the millimeter wave, and then for high precision in general for multiple target and multiple user rate. So this is a little bit what we have that it's in a sense published. Okay, so what we are doing today in my lab. So what's the follow-up? Okay, so this is some of the stuff, the topic that we are kind of working today, and we'll spend a little bit of time. Very actually component that you have. We know about range. Our case, we optimizing, maximizing the signal-to-noise ratio. There's a one of the what I know is actually to consider rate for the communication part, and then to consider some kind of Kramer-Rao lower bound for MMSE, or a bound or estimation for MMSE minimum square error for the estimation bound, and see how you can actually optimize the two. increasing the SNR, and the SNR is linked to both the rate and to the error. Precision of R2. And we did to the ortho decision. It's still out there, but I think it's back. So, like the reality of it, detecting, and it's a car will reflect back a cluster, not one path. And if you're trying to use the technique we have here, which is trying to detect every path that gets back from that car, you end up really pushing the limit, and music will not work. Matrix will not work. It depends on the number of the chain, and if the car is reflecting back 5 or second, whole thing, the whole thing. Trying to evaluate that both for the self-interference cancellation, because even though it's not mentioned obviously here, but when we're doing self-interference cancellation, you want to cancel the multipath that you don't want, but you want to keep those echo of the sensor, the target that you're detecting. And that's in itself is not easy, because they're all multipath in some sense. So the multipath and self-interference have to be done properly, but also the cluster from the object you're detecting has to be also updated into more a cluster. It's not one signal setback. But I would say, and this is really especially for, this is the last topic, the full millimeter wave. This is all good as long as it's simulation, or you can kind of do a little bit of test bed at home. But I think the implementation on a chip is absolutely needed and fundamental. And for millimeter wave, none of that is easy. So the real impact of all this nonlinearity, how you can do this analog cancellation, how you're saturating or not you're saturating the receiver, how far you can go in terms of precision of analog to digital converter, all that has to be actually verified, and that there's no way around it unless you do kind of the transceiver, the chip level, especially for millimeter wave. So that's also something we start working on with a collaborator who knows more than me how to do this, but it's definitively an interaction of these two fields. You have to go at all to the implementation level to be. So this is a little bit what we're working on in terms of integrated sensing and communication, my group. So just a little bit of thankfulness. So I think the part that it's full-duplex integrated sensing and communication, the most important collaborator are my previous PhD student, Atiq Islam. He's at Qualcomm now, and then previous collaborator, George Alexandropoulos, who's a faculty at the University of Athens. The full-duplex part, partially the analog, the inherent self-interference part, this is a work with my also two previous PhD students, Farhat Farzami and Sayran Kaladian. So they work all in all this, the hardware, the RF, the building the system, the test bed and the lab. They really helped a lot with the RF and the physics of the system. Sayran is with Microsoft and Farhat with Motorola. And then we have a new student, so they just joined. Mohammed is the one that would be working on the cluster multipath, especially for the case of vehicular network. And Atahar Shams will be the one working on the benchmark, the performance, the best performance ever, and how we go further. So thank you very much. Any question? Yes.
Very good talk. Just out of curiosity, I've been sort of away for a while. the multipath problem.
Mhm.
Is there any model that's being used right now in the, particularly in mobile communication and such?
I think, yes, there's a lot of model. I think,
It used to be like Jake's model.
I know, I think we're far from Jake's model.
Yeah,
That's what I studied at school.
This was when I was working.
Yes, exactly,
This
yes.
is a long time ago.
Yes, yeah, no, definitively. I think this,
But if that is the case, then
Yeah.
have you guys thought of maybe using like angular diversity? In other words, instead of trying to accommodate all these things.
Yes.
Across your MIMO.
Mhm.
Perhaps try to kind of divide your resources and use them to actually sort of accommodate. Because as you just said, some of the reflected, some of the secondary rays and
Yeah.
things can be useful
Yes,
in
exactly,
a sense.
yes.
Where, for instance, I remember in digital communication, in, the Bell system, microwave system, we used to use these angular diversities.
Yes.
Actually,
Mhm.
which was quite a bit of actually,
Yes.
quite a bit of an investment in terms of, relative to spatial diversity.
Yes. No, you are right. There's actually theoretical work by, I forget the name of the professor at Rice University, but he actually proved that the multipath can even help in the sensing. So not only we know it helps for communication, we use for diversity. It's an extra link that gets from the transceiver to the receiver. So instead of fighting it, just use it to your own advantage. But we actually have a proof that actually it helps for the sensing too. Having multiple path for the sensing will helps too. I did not do it, but it's definitively one good direction. Is some of the stuff we need to consider. Absolutely, more realistic model of multipath, and that you can do different models today. I think you have the ray tracing models with machine learning. So that's definitively something we should do. So great question. Any other question? Yes.
How do you measure the self-interference channel? Because if the self-interference is too strong, your elements will be saturated, right? So,
yes.
How is the measurement done?
We do not measure it. We try to cancel it before it gets it. So usually it's the beam. So the first thing we do is toward the beam. So when you transmit, especially for MIMO, so if you talk about MIMO, I think, so you go to the beam in the sense that the null, you know how the beams are most of the power in one direction, and the null is toward the receive antenna. Okay.
Yeah.
But what do you mean measuring it? Maybe I'm missing the point. Yeah, go ahead.
So what I was saying is, for example, we are assuming near field line of sight channel for the self-interference, and we are canceling that.
Yes.
Forming, right?
Yes.
What if that model is not accurate, so your beamforming doesn't work well?
Yes, I mean, if there's a multipath or it's not really accurate, yes. I mean, so that's why we need the beamforming to adjust to whatever we are receiving. But you're raising a very good point. That's really a challenge when you do sensing and communication. Because in communication, I would say I don't care about whatever multipath. I'm canceling everything. I don't want any self-interference. I don't want an echo coming back to the system. That's not happening. But in the sensing, unfortunately, no. Some of the echo is actually the one I'll be using to detect the target. So it's an important question. So far we did not get there, but it's definitively a serious question to consider. Yes, and it's trade-off that needs to be done. Yeah.
What is your opinion about if you're doing signal processing work, like this work, for example, you have just presented? If you have algorithms that work well with, let's say, this self-interference channel,
Yes.
even different parameters to the model that you have, you really need to go to the circuit level and study how it will work in a particular circuit, or you assume that this will work well in general?
Yeah, I think it's a good point. At the end of the day, if you want something that actually works and it's not theory, what level, frequency, antenna, architecture you're using.
Problem, if that is the case, then the problem is that we don't have a good model for the interference channel that we can exploit.
That's true.
When we are using algorithms.
Yes, that's true. And I think absolutely that's testing. That
arrays, or you have correlated arrays for transmission and receiving.
Yeah.
It's kind of like missing that part.
Yeah, no, I agree. And I don't know, I mean, the solution, of course, in terms of just a short term, I think machine learning can help a little bit when you're not very sure about whatever algorithm we're using. But yeah, I see, but again, I think sometimes I feel when I go closer to the RF and the circuit level, we live a little bit in different worlds. Communication theory people, we have a lot of modeling. We know a model, we have a lot of kind of fixed model. This is how channel should react. This is how you have, and this is how you solve it. RF and circuit, I don't think they have much of modeling, and I don't know how much they believe in modeling in some sense.
But the truth is also that if we just work, we could use as a interference channel that
Yeah.
we generate with one of these tools to simulate.
Yes. Yes, the
full-duplex
measures, yeah,
receiving
exactly,
array,
yes, yeah.
Measures of interference channel. I can evaluate my algorithm with that, but that's also very incomplete.
Yes,
because
absolutely.
It's even maybe worse.
No,
It's
absolutely.
kind of like.
No, absolutely true. And then, yeah. And to be honest, the part when I get into the implementation, the first self-interference, the coherent interference counselor, we did not know at the time how much tuning is needed, because actually when you walk by the antenna, the whole impedance change. And this is for communication person. We did not know, I did not know that before. But then really the needing of the tuning all the times, depending on the environment, is really something we don't have in communication theory models, yes. And I think that's why I believe this research between the two, I think we can help them by trying at least to get some model. At least this is my hope.
Yeah.
Because otherwise, from my point of view as a communication theorist, it will be too boring to just build the system, test it, see if it works, tune it a little bit, it works, go next. I want to see what is the optimally possible, what is the best performance ever, and how can I get there? So it has to be a work both sides, yes.
In your block diagram for the full-duplex self-interference cancellation, I saw that you had a impedance mismatch.
Yes.
Block. So
Yes.
are you intentionally creating impedance mismatch to cancel out the reflected signal towards the transmission and just focus on the receive chain?
So for that one, we are canceling the self-interference inside of the circulator in some sense, okay? So it's not really the outside. So that's in the case when you have the same antenna is transmitting and receiving. So it's a cancellation of the leakage inside of the circulator. So I don't know if we can call that multipath, honestly, I don't know. But that was the purpose. So there's no exterior multipath. We never tried to cancel any extra multipath with that, but that's something to consider too. Yes.
But isn't the subletter doing the job of not why do you need an extra block between subletter and the antenna? Is it?
Yes. So the mismatch is a block, between the antenna and the circulator. Yes, to do the little bit of mismatch. Yes. Is that your question, or it's?
Because normally we would try to match the.
Yeah, perfectly. Yes. Yes.
Perfectly.
Yes.
You are intentionally creating mismatch.
Yes, exactly. Yes, that's exactly what we're doing. And by the way, I think I did not mention that because we are intentionally creating a mismatch, the received power is off because we're not optimizing the received power, but it's really by small percentage. So it's worth really canceling the self-interference with a small percentage received power. And I do not remember the exact number, but it's in the paper. But it's really very small. I don't think I mentioned it. Yes, no problem.
Some more online here. See any questions online? All right. Thank you for your talk.
Thank you very much. Appreciate it.
Hi, I'm Greg Bottomley.
Nice to meet you.
Nice to meet you. I'm sorry, I should have come in person. I watched online,
Okay.
but I wanted to meet
So
you.
what is your research you're doing?
So I'm actually semi-retired. I've stopped researching. I used to work for Ericsson.
Okay.
So I recognize you worked with Sylphian.
That's true. Oh my
So
God, you're from an old life
I'm
of
from
mine.
the old generation, so I worked till 2009 the Great Recession, and I had to switch industries.
Yeah, yeah.
But I worked with him through the Vehicular Technology Society.
Yes, he was my PhD supervisor.
Oh, okay.
Yes,
So
yes,
yeah,
yes,
yes.
of course.
So yeah, I'm from those old days, but
Yes, yes.
but even in those old days, I remember there was a group in China trying to do full duplex communications only, no sense.
Yeah, yeah, yeah.
And it was tough because, as you pointed out, the power.
Oh, the power.
It's
is
just so
like-
different.
Absolutely, yes.
And it's really neat that you've considered sort of both the analog world and the digital world in dynamic range, so that you can't just digitally cancel it like
No.
we maybe hoped.
I mean, there's a push to do everything by beamforming and then the rest, but I really don't think it's work. I mean, it depends on what kind of equipment that you have, but I don't think it's in general.
Yeah, what if your beam accidentally hits something close by and bounces back?
Yeah, exactly. The whole thing goes. If you think millimeter wave now is not stable, imagine you add full-duplex on it. No, I think
So
that's-
this is really interesting. And also, I mean, the promise is like twice the, if you're just doing
There's
communications.
no drop. I think.
But you showed you don't really get
I'm not.
twice.
No. I don't. I think I stopped saying we get twice. Oh, this is the thing. This is the thing about twice. I have to tell you, it's true that if you see bidirectional, you can say twice. But besides that, of course, you can never cancel the set interference completely. Even when you're sending at the same time, you have to have a conservation of energy success. But now you're sending over the whole bandwidth all the time, both ways. Just by that, you're not having double, if you want to be fair in terms of energy and everything. So that's by just that constraint, we're not getting the two.
Okay.
But what I tell my students sometimes, think about this way. If you have a relay, actually multiple relay in a communication, this is transmit and receive. If you put full-duplex, instead of those relay like sending, waiting, sending, it takes forever to get the
Yeah.
message. If they use full-duplex, actually that gain is not two, is more than two. So two doesn't make any sense. So I never used, it's like, I'm not using the two ever. I'm out of the two. Whoever writes two out, none of my students is allowed to write doubling, any two, no. Because it's not true in any sense. It's not the number.
But you're still getting interesting games. It's
Yeah,
exciting.
and I think it's better to be realistic than to say, oh, we're doubling the spectrum efficiency. I don't think we're there yet. but-
Well, you're being honest. Well, nice to meet you.
Thank you very much. I
Enjoyed your talk.
appreciate you. Thank you. Hi.
Hi, Dr. Smida. And I'm in my supervisor is Dr. Winnie.
Okay.